Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Good afternoon. My name is Alexandra Dil, as Stuart said. I am from Argentina, from the computer science of the University of Buenos Aires. And today I'm going to present my work on 3D geographical environments and geospatial data exploration using flight simulators and geodatabases. The title is a bit longer, but I promise you the presentation will be shorter. Yeah. This work consists in the integration of three technologies: geographical databases, flight simulators, and scientific visualization to do both analysis, quantitative and qualitative analysis. And this work could be enclosed in the area of geographical visualization or geo-visualization that has several subjects of interest: the exploration of geographic phenomena, global climate changes, also prevention of environment disaster, ecological studies, etc. And the integrated process has three main parts. The first part involves the management of heterogeneous information sources. These data sources could come from different sites, could come from terrain elevation data, topographic information, and other geospatial data sources like GPS or remote sensing. And we have to unify this heterogeneous and different formats. And the second part of this work involves the management of this information, this massive volume data information, and to put into a database, a geographical database. And the third part of this work is the visualization and simulation of this information. Geovisualization is not only to show data, if not, it consists in explore data in the way the user can indicate where to go and what to see. And we will try to achieve this using flight simulators. Also, another geospatial data could come from other applications directly to the visualization system. We have between both the two last parts an interface to create the eScience to the visual application. In this work, we have used a data source coming from the SRTM, the Shuttle Radar Topography Mission, also Landsat images, and we have studied the weather data, the climate data, from the National Climatic Data Center. And we have defined an interface, a unified format to manage these data sources. We have studied the standards proposed by the Open Geospatial Consortium. The UGC proposed define the OpenGIS standards and to store and to manage geospatial information and to exchange this geospatial information between several applications. And we have a study, a language, the geographic markup language that this standard proposed. Here we have an example. This standard proposed two ways to use this language, GML. We could use templates, or also we could use profiles. Here I have a profile, a point profile, and we could indicate the spatial reference system. It consists in a EPSG code. This code is defined by the European Petroleum Server Group that has a database with all the coordinate systems, and define also that this coordinate system is a geographic coordinates system and use the datum WGS84. Here we have also the coordinates, the latitude and longitude coordinates, and an identification of the feature we're modeling. And we have also studied another standard, keyhole markup language, that was firstly used by the product of Google Earth, and then was adopted as a part of the GML specification. KML is used for a wider community, also scientific community, that upload information over internet using KML. Here we have an example of how the Open Geospatial Consortium exchange information of the spatial reference systems. The second part of this work is the construction, consists in the construction of a topographical data model. And for this reason, we have studied three of the most popular flight simulators: Microsoft Flight Simulator, Flight Gear, and X-Plane. And also we have studied the standard OpenFlight to create and to share scenes between flight simulators. And we have built our model. Here we have a representation of the high-level information. Our model was inspired mainly in OpenFlight, but also has several features of the others topographic model, and divides the Earth in areas. Each area is bound by a coverage and has his spatial reference system. It contains one or more layers of information. In our work, we have modeled terrain information and weather information, and also this area could be divided in a reticular grid with depending on the level of detail. and each cell of this grid is modeled as a tile, and the tile contains information about the extension of this land. Also, we could put information about the projection we decide to use, for example, Mercator projection. And each area has a model list. I put the other part of the model in the next slide. A model list contains one or more models. We have modeled only point-based objects at the moment, and each model is composed by one or more components, generic components that has their own local coordinate system and its bounding box. And in this way, we could model any object without put the semantic of this object into the model. And each component has its geometry, and we could have a mesh and light point face. And if this component use faces, its face can be applied in a skin. And this way, dynamically, the appearance of the component could be changed depending on the level of detail. It means the distance between the component and the observed viewpoint, and we could adapt this skin of the component while we are flying the topography. And well, we have implemented this model in a geographical database. Geographical databases allow us to do special operations, and has special data types like a point, line, string, and polygon, and has also an spatial indexing. We have chose PostgreSQL. PostgreSQL use spatial indexing called GIST, that is like a R3 but has another features to improve it. And we have chosen this PostgreSQL database management system and its extension PostGIS because it follows the OpenGIS standards and also allow us to set up and to change the spatial reference system that we'll want to use. And the third part of this work is the integration of all this model data in a visualization system. For this reason, we have studied the previous work, and there are few previous works that integrate flight simulators and geographical databases. I can mention the work of McDonald's et al. And that is a It has a eco flight simulator integrated with the application and can explore the biodiversity, and also Google Earth, that in the version 4.1 of this product added a flight simulator. In this way, anyone can fly over the topographies and the sceneries that Google Earth show us. And this is a very important point, because what we are trying to do is to build integrated tools to visualize, explore, to analyze, and to do a synthesis of this huge information, and in this way promote insight to other areas like us, Earth areas of study. And our visual system was implemented using OpenSceneGraph, and that is a high-performance 3D graphics toolkit to generate real-time scenes, and it is very used also to implement flight simulators, and it was used in the Flightyear open source simulator that I mentioned before. And this tool is based on OpenGL and Microsoft Visual C++. I have used Microsoft C++, and also I have used Blender, the Blender visual application, to do the models and to map the Landsat images into the topography. And also I have used Python to import CRTM to do the interface between the systems. And this is a panoramic view. In our approach, we propose not only a panoramic view, because there are a lot of applications that show data into the 3D, but I will show you what is it. This is a tile of 1 degree by 1 degree, centered in this latitude and longitude. It is a small area of Bahia Blanca city in Argentina, and it was mapped Landsat 7 image over the topography, and the data of the SRTM is have a definition of 3 arc seconds of latitude by 3 arc seconds of longitude, and is modeled with a WGS84 datum and with geographic coordinates. And also there is a layer of climatic information. This weather station, we could see it in the next slide. Here we have the weather stations, and these are, because of the small tile we have modeled, and these are fictitious weather stations. We have not many weather stations in this zone. And we have this weather layer was modeled by using a Delaunay triangulation, and we can choose in the application the opacity and the level of subdivision of the weather layer using finite element method. And here we have the other view I mentioned before, and this is a challenge. Try to not only show the data in a panoramic view, if not, I could not just blur this information. This is a video. It has, I know, a low frame rate now, but the application allows us to implement the core of the system into the GPU. We hope to allow real-time frame rates. And well, as a conclusion of this work, we can outline the main features, the main results we have obtained. We have defined a GML unified interface and constructed a generic since this generic, flexible, and extensible data model. Generic because it allows us to model generic point-based objects, and also to define flexible because it allows us to define several layers. It uses inheritance to model the layers and the geometries. We can add another geometries, and the PostgreSQL database allows us to model, to implement this inheritance also. And we had constructed the 3D visualization application, and added a flight simulator to begin this challenge of show data and explore data in an interactive and immersive standpoint. Future works will be the integration of other heterogeneous data sources coming maybe from KML, because there is a wider community, scientific community putting information. You can mention the UNESCO and others, very big and important communities. We will continue to adding another features to the visual system, like as level of detail, to a more realistic visualization and multiple coordinate system, and also new data layers of information coming from especially climate data sources like gas, wine, and speed. Thank you very much. That is all. Thank you.
Thank you very much. Any questions for Alexander? I had a question, Mary, to kick things off. I was a little clear in the beginning whether the system is being used by environmental scientists today, or whether at the moment it's a computer science project. Do you have people trying out the flight simulator that are scientists today?
Not yet. No. At first, the project began as a bigger project involving national agencies, and then this turned to a more green research area, and we hope to work more until or before to present this to maybe climatic agencies or someone that could be interested in it.
Has the work been published to those that community?
Yes. It is published in the image processing group of the computer science of the University of Buenos Aires, but everyone that want to or would like to contact me, please just do it. I can send you more information about it. Okay.
Any other questions today? I had one more, perhaps parochial question, local question. We have a member that used to be with the flight simulator team in Microsoft, in the external research team. So
Yes.
I don't know whether you're connected, but we should.
Yes, perfect. It sounds good.
A good contact.
Okay.
Okay, well, thank you very much, everybody, and thank you especially to Alexander and Paul.
Thank you. Thank you very much.